Welcome, everybody. It's my pleasure to introduce Dr. K.B. Subbalakshmi from Stevens Institute of Technology. She'll be presenting updates on her research task WRT-1017, keyphrase extraction using language embeddings, phase 1 and phase 2. And with that, I turn it over to you, Doctor.
Thanks, Tyler. Thanks, Todd. Good afternoon, everyone. So today I will be talking about key phrase extraction, specifically using language embeddings. And I am a professor in the EC department at Stevens Institute. We can go to the next slide. Okay, so key phrase extraction is essentially the problem of you have a big document and you're trying to understand what the document is talking about using just a few phrases. Right. So this is a very important step in a lot of downstream NLP tasks, especially things you would need in competitive intelligence, like trying to understand what kind of articles are relevant to an SME, a subject matter expert, ranking ideas according to importance. So you can take a bunch of documents, find the key phrases from there, you get an idea of what the ideas are, and then try to rank them according to some importance. Extract trends of what's happening in the general area of interest, discover areas of interest, and create summaries of documents. Next slide, please. So our goal here was to propose new key phrase extraction algorithms, specifically using embedding language embeddings, which meet or exceeds the SOTA methods or the state-of-the-art methods. And our goal also is divided into smaller sub-goals. One is that we want to balance the diversity of key phrases with relevance. What do I mean by that? Well, we can have key phrases that are very close to each other in meaning. And so having 10 of those is not going to give you an extra in-depth idea of a document, whereas having them be as diverse as you can while still being relevant to the document, that has more value. So trying to get something like that of a balance between diversity and relevance is important. We use the title of the article as well to inform the key phrase extraction, because in most cases, the titles are constructed so that it catches people's attention. It talks about exactly what the rest of the article is in as concise a way as possible. So definitely the title of an article has information and we'd like to use that. The third is to use language embeddings, which are essentially a way of looking at everything in a language, like a word or a sentence or a phrase or a document, as a multi-dimensional numerical vector in some vector space. So that has an interpretation that if you have two vectors in this multi-dimensional vector space that are close to each other, in real life, those two language units, maybe words, maybe documents, maybe sentences, have a closer connection between them, maybe meaning or something like that. And then we also suggest a novel way to construct a key phrase. Next slide, please. So the main innovative aspects of our algorithm is that we are using the title information. So we are basically looking for the similarity between the title and the key phrase, and the key phrases that are closer in relationship to the title will obviously be more relevant to the document. We use the frequency of key phrases as one of the indicators. So for example, if key phrases, important phrases will land up appearing more often in a document. So if we find very highly frequent key phrases, we'll just use them directly as a key phrase. Then we suggest new ways of constructing a candidate key phrase. And then we suggest a new metric which will do this trade-off between the title similarity and basically the similarity and the relevance of key phrases with the diversity factor. So next slide, please. Okay, so this manila envelope here represents any document. So from that entire document is fed into what we call the candidate phrase selector, which is something we construct based on how we construct our candidate phrases. Next, yeah. Then we send that all the candidate phrases that we select based off of our method of construction of phrases are sent to this thing called Universal Sentence Embedder. The document and the document title are also fed into this Universal Sentence Embedder. This thing was done by Google, and what it does is represents every language unit as a point in a 512 dimension space. So in this little cloud structure, the cloud thing is supposed to be our 512 dimension vector space. The yellow triangle can represent, say, the document. The blue diamond represents the document title. So each of those things will be a little vector in that space. And then all the little dots that you see are the embeddings of the candidate phrases that we have done, that we've come up with using the candidate phrase selector. We define 3 different types of distances that you can see written up there. DDoc is the distance between a candidate key phrase and the document, which means it basically captures how closely this particular candidate phrase represents the document. DP is the distance between the candidate phrases, and this will capture how close the candidate phrases are to each other. So if they're too close to each other, then you probably don't want all of them. You dump a few of them. And then DT represents the distance between the candidate phrase and the title, and that's again the sort of relevance factor. Then we use all of this to compute this metric, which is beta times DDoc plus DT plus 1 minus beta times DP. So beta is our parameter that trades off the similarity between key phrases with the relevance. Then using that metric, which we will calculate for every candidate phrase, we will rank and choose the highest n number, which you will specify. Yeah, I want 10 key phrases from this document, then you just choose 10 of those. So as I mentioned before, we'll also be paying attention to phrases that occur very frequently. So those highly frequent phrases will be directly passed out as a candidate key phrase. So one more mouse click. So this is how in the end you will get a bunch of key phrases, and it will give you a sort of color coding if you want it. This is a heat map, which basically shows how high the rank is for that particular key phrase. So if it's red or redder, then it is warmer color means higher rank, so more desirable, and cooler color means lower rank and therefore slightly less representative. So from this, you will just pick the n number of key phrases that you want. Next slide, please. Yeah, so what is our new way of extracting key phrases? Well, we define for our work here a key phrase as something that contains 2 or more words. And how do we define those 2 words? It's usually an adjective, 1 or more adjective plus a noun, then followed by a noun, and then a noun followed by a noun, okay, 1 or more. Verb n followed by a noun. Example, distributed system. And then an adjective and a verb, gerund and a noun. Example, minimal generating sets. Then adjective, VBN, and then a noun. So out of print music. So this is different compared to what one of our competitor algorithms does, which is called EmbedRank, and they just use 0 or more adjective and 1 or more nouns. So we have a more comprehensive makeup for key phrases, which we believe, especially for scientific documents, this works a lot better than just doing an adjective and a noun. Next slide, please. So then once we have these candidate phrases, we look for words that are not really special, like, things like such, more, other, most, less. These kind of things we just use them in regular language. They really don't represent anything specific. They definitely are not part of any key phrase. So we'll trim those things off. So for example, your automated, go back please. Automated key phrase generation might have come up with the phrase such information architecture. Obviously, such is not a key phrase, so you drop that and then make it an information architecture. This is also automated. We just construct a dictionary of unimportant words and just pull them out. Then we compute high frequency key phrases, like I said before. Simply count the number of potential key phrases, find the ones that are 2 or more times, and output them directly. Next slide, please. The third step is the actual language embedding, where we specifically use sentence embedding, which is versatile enough for us to modify it for phrases and for titles and for documents. And like I mentioned before, we are using the one that's proposed recently by Google, and it either uses a transformer architecture or deep averaging network. And it is considered SOTA for language embedding. And then it produces a 512 dimension vector for each of those phrase, document, sentence. Next slide, please. So here is, by comparison, what happens with the EmbedRank, which is one of our comparison algorithms. This is an unsupervised method, just like ours, to automatically extract key phrases from a document. And it uses sentence to vec, which is another way of transforming a sentence to a numerical vector, but it's not the state of the art. But that's not the only modification, obviously. We changed the way we look at key phrases. We changed the metric. We use title. We have made a bunch of other changes to this thing. So here you can see this beta parameter here, this metric with the beta parameter here. Here, this beta just only trades off similarity of every phrase to the document with the similarity between them. Ours was a little bit more complex. And then it does a rank and select. Next slide, please. Okay, so the metric that we proposed was this one here. It's a new metric, and it trades off the relevance of the key phrase, and it's a similarity, like I said before. So we use a normalized similarity document measure, which means it's a normalized cosine similarity between the document and each of the candidate phrases. Normalized similarity with title, which is the normalized cosine similarity between the title and each of the key phrases. And the norms in between is the between key phrases similarity. And beta is the thing that kind of trades off. So if you have higher beta, then you're giving more weight to relevance. If you have a lower beta, then you're giving more weight to being diverse. So we balance those things off. As beta is a parameter that we will tune. Next slide, please. So once you have that metric and you calculate that for every possible key phrase, you have now a numerical way of comparing key phrases. You just rank them, excuse me, and pick the top n key phrases as your key phrases. So we use different methods, evaluation metrics, because we are using two methods. Although I have to say one of the methods we are comparing against is not a fair comparison for us. I'll explain that a little bit later. Next slide, please. So the first evaluation method is by using precision, recall, and F1 score defined like this, where the precision is defined as the number of matching predicted key phrases, meaning how many of the key phrases that you predicted match what the author gave, divided by the total number of key phrases you predicted, meaning how many key phrases you generated. Recall is number of matching predicted key phrases divided by total number of ground truth key phrases, which means first one is the numerator is the same. Denominator just means how many key phrases the author provided. F1 score is 2 times precision times recall divided by precision. So it's basically precision times recall divided by precision plus recall. These are standard metrics that are used in the literature. So next slide, please. Yeah. So here is our comparison. N here, the first column, refers to the number of key phrases that you're generating. So it's 5, 10, 15, and so on. EmbedRank, we mentioned what that EmbedRank algorithm was. So that's one of our comparison metrics, comparison methods. And then another one is called multipartite, which is another way of generating key phrases. INSPEC and NUS are 2 data sets that we ran this on. And as you can see, ours is the current proposed one. And the red one has the highest values on everything. And we beat these other methods pretty solidly, which is not surprising given all the other enhancements that we've made to it. Next slide, please. So this evaluation method was done because we wanted to just for curiosity's sake, we wanted to see how we'll compare with a supervised embedding, supervised key phrase extraction. Now, supervised anything learning is always going to give you better results than unsupervised learning. That's how it works. We just wanted to see how close we are to that. And so and because the paper that we were comparing with had a slightly different metric for measuring performance, we changed the metric so that we'll be comparing it against the right metrics. So the precision was the number of predicted matching predicted key phrases divided by total number of predicted key phrases, same as before. Recall has a slight change where you are dividing the denominator only uses number of ground truth present, which means, so to go back, what does present key phrases mean? Well, an author can write a paper or write an article and then give you key phrases, and that key phrase may never actually appear as a key phrase in the paper, but it's still a key phrase. It describes what's happening. So a key phrase like that is called an absent key phrase. A present key phrase is something that actually physically appears as is in the document. So now we are only looking, the denominator only deals with the key phrases that are actually present in the document as is. So F1 score, same as before, and here's a reference for the paper we are comparing against. Next slide, please. So to our surprise, ours is the bottommost column here. To our surprise, for one data set, INSPEC, we actually beat all of the supervised key phrase generation technique, and we were really surprised about that. We didn't expect to be doing that well, actually. The other data sets, we don't do as well. We're not too bad, but it's obvious that we are an unsupervised key phrase extraction method, so obviously we're not going to be getting as good results as the other guys. So, and here there are again, within each INSPEC, CRAP-EVEN, NUS, SEMIVAL, these are all data sets. And F15 means doing the F1 score for 5 key phrases, F10 means for 10 key phrases, and F1X denotes the number of ground truth key phrases present in the original document. And that'll obviously vary with each document. You cannot fix one number and then do it. So that's a little bit different there. Yeah, so next slide, please. So strangely for INSPEC, our method is actually beating everything, including supervised models. For the other data sets, our method is better than unsupervised for certain cases, for unsupervised across the board, but it is close to some supervised models and better than some others. So next slide, please. We were curious about this and we wanted to see why this might be so. So one of the things we thought was maybe the way we designed these key phrases, like how we changed it, may be affecting it. So we looked at INSPEC and we looked at all the 4 data sets, and for each of those we calculated the number of ground truth key phrases overall for the entire data set, and then we found the number of single word ground truth key phrases. In INSPEC, it's like 13.76%. In SEMIVAL, it was 161, which is 23.99. For the other two, it's those percentages over there. Number of overlapping ground truth key phrases, meaning key phrases where some part of the key phrase is actually present in another key phrase. And we are showing you how that number changes as well. And because of the way we constructed key phrases, where we force it to be 2 or more words, we will not do well whenever there are too many single word key phrases. So in INSPEC, the data set, if you see, that's the lowest single word ground truth key phrase we find, which makes sense. So that's probably why we're doing so well with INSPEC, whereas not so great with SEMIVAL and CRAP-EVEN. Even so, it doesn't fully explain why our unsupervised method should be beating the supervised method. We still don't know why. Those are some of the things we will be looking at for the next cycle. Looking at that and then looking at seeing other ways of generating key phrases. So that's pretty much it for me. Happy to take questions.
Thank you for your talk.
Thank you.
It doesn't look like we had any questions in the chat, but maybe I was wondering about how the if you could speak a little bit more about the effect of the scale of the data set on the results. And I noticed here that, yes, thank you.
Sorry, was there someone else?
Oh, no.
Okay. So the scale per se does not affect it. So INSPEC, I don't have the number exactly. It's a pretty huge data set. INSPEC, NUS, these are pretty big data sets, and they are standardized. So which means if you give results for these kind of things, it's generally considered legend. So the scale of the data set itself didn't give us any big difference, but the kind of key phrases that were present, key phrases given by the author that were present in these data sets, that seems to have made a bit of a difference, because we decided to define key phrases as having at least 2 words, whereas some authors just gave a lot of key phrases that are just 1 word. So when you have 1 word, when the ground truth has too many 1-word key phrases, our algorithm is not set up to catch those. So in those cases, it wouldn't do so well. But that might be why. So our performance is across the board for all data sets for unsupervised learning and unsupervised key phrase extraction is good. But how good it is depends on these little characteristics of the data set, these little vagaries, if you will. Yeah.
Well, this room will be open until 12:55 if people want to stay in chat.
Yes. So how does the whole procedure work?
Todd, could you please?
So usually we would be waiting for questions and answers, but I don't see anybody giving any questions and answers,
right,
presenting anything. So let me talk to Maya real quick, and I'll be right back. Hold on.
Maybe if I could ask a little bit more about the challenges of trying to adapt maybe some of the standard natural language and processing techniques to more technical documents.
Yeah, it is a big challenge, because the way one constructs phrases for technical documents is so different from ordinary ways in which we speak. So that was figuring out exactly how we would like to construct the key phrases was itself a chore. Apart from that, there was also this strange things like, when you're, and more nitty-gritty kind of things where some of the standard available tools that you have for even pre-processing NLP wasn't doing so great. All this stem lemmatization tools and this and that. So we had to do several tries with several different toolkits before we even could pre-process the scientific documents. And the other interesting thing so this is all standardized data sets, and that's good. But CCDC also gave us the task of actually collecting data set, which we haven't presented here. They gave us a task of also collecting data set that was of interest to them, from journals that were of interest to them, and then doing the same thing. And the challenge there was, the way the document was constructed was all over the place. Some documents had abstract, some didn't have any abstract. The formatting was so different, and some had author provided key phrases, some just didn't. So you would have to remove all the things that didn't have key phrases just when you're testing and training, right? Because how are you going to evaluate if you don't have any ground truth to test with, right? So after we've done all of that, then we work on the documents that didn't have any key phrases from the author, and then we hope that worked for it. So there are quite a few challenges especially when we were working with the CCTC provided data set, which is not standardized, and that's a whole other ballgame dealing with that, and just even the logistics of converting it from a PDF file to something that you can actually work in your, feed into your algorithm as data was a chore, because I'm sure anyone who has copy pasted from a PDF onto Word or even text document, how many weird things happen in the text, right? So we had to deal with all of that, cleaning all of that. So it was just,
We just got a question here about general insights or lessons learned from the testing and evaluation process that might help others guide with testing machine learning solutions.
So testing machine learning solutions in general, it's always easy. I would always, after we learned that lesson from trying to do CCDC directly, we realized that we have to start with the standardized data set, simply because we won't have to deal with so much pre-processing in the beginning. Some data sets even in there are clean, some are not so clean. But compared, the magnitude of effort that you have to put in to get that data clean data is a lot less for standardized data sets than this one. Other things I would say is, your parameters, like finding your parameters, getting your optimal beta. That's not a normal, like that's not you just don't do a linear search for it or anything like that. So it becomes a very ad hoc process, and you do that a gazillion number of times, and it is all time consuming. It's all resource consuming, and there's just no way out of that. You just have to keep going until you find a parameter that works, at least a local optimum. So that takes a lot of effort. What else would I say? Yeah, if you're dealing with NLP related tasks, I would not assume that the NLTKs and the standard processing tools that you have is doing the right job. So we had to switch our tools several times, and that's like each epoch, each run of the simulation was taking a few days. You finish the entire data set, and then you realize, well, this thing has. So you go back and you look at the key phrases, right? Just randomly pick a few. You're not going to do for 10,000 documents. You're not going to look at every single one of them, but you will make a random sample of the output and then look to see if it's all legit. And we found some really strange things happening in those key phrases in our first few things, even though we were using standard off-the-shelf NLP tool sets. So we had to go back and then change to OpenNMT. So, and that seems to be working much better. So I would say, don't assume that just because there is a package available that it's actually doing the job that you think it's doing, or that it's doing it well.
Maybe I can ask, were those odd key phrases? Would you have been able to guess from the statistics, or do you really have to open up the?
You had to open up. It was not even a key phrase. That's the funny part, because it was doing. It had a lot of lead underscores and random things in the middle, like weird characters, and then sometimes it would just go dump, like the program will die, and then you're like, okay, why did this happen? Because it's looking at a junk symbol that we never thought is going to show up in a text document, right? So that kind of stuff happened. Yeah. So some of it you can catch because thankfully your program will dump code. And some there's just no other way, but you have to do some random inspection.
Great. Well, thank you for your time in addressing those questions and for the presentation.
Thanks.
Like I said, there's